Welcome to the Paul G. Allen Distinguished Lecture Series for 2024. It's my pleasure today to welcome our today's distinguished speaker, who's Ryan Williams from MIT, who's a professor at MIT. Ryan did his PhD at Carnegie Mellon University, and then after prestigious postdoctoral fellowships at the Institute for Advanced Study and IBM. He was a professor at Stanford before joining MIT. Ryan has won many awards, including a Sloan Fellowship, an NSF Career Award, a Microsoft Research Faculty Fellowship, a Thornton Faculty Research Innovation Fellowship, and most recently the 2024 Gödel Prize for his work. Ryan really is known for taking diverse areas and making connections to make surprising breakthroughs in the field, and his Gödel Prize was for research that broke a 20-year log jam in our understanding of circuit complexity. So please join me in welcoming Ryan.
Thank you for the very nice introduction. I hope I can live up to that. I'm grateful for the opportunity to speak to you today. The content of my story is going to be mostly mathematical. It's theoretical computer science. But it's also personal. And there are quite a few meta-level points, too, which are broader than the content. So I hope they'll resonate in some way, even if the theory stuff is not your cup of tea. And there will be theorems stated, but I'll do my best to make it gentle, and please ask questions as you like. So our starting point is one of the most fundamental problems in computer science and mathematics, the P equals NP question. And just to remind you, NP is a set of problems where verifying a solution is easy to do, and P, roughly speaking, is a set of problems where finding a solution is easy to do. And our notion of easy is polynomial time. There's some algorithm solving the problem in some polynomial in n number of steps on all inputs of length n. Okay? And one of the best ways to illustrate the difference between P and NP is to consider the problem of factoring integers into primes. So I give you this very big number, and I want you to factor it into some x and some y. It turns out this can be factored into this prime x and this prime y. And if I gave you x and y to begin with, right, it's easy to check that x times y equals the given number. But not having the x and y, trying to find the x and y, is very hard. This is RSA 768. It took approximately 2,000 CPU core years and a team of number theorists and programmers to find this x and y. So there's clearly a difference between verifying once given the answer and finding. And just to give one more example, suppose I give you a slightly larger number and ask you to find the x and y. Well, someone cooked up this x and y, but publicly we don't actually know what the x and y are here. And it hasn't been factored, as far as we know. Okay. But there are people working on such things, and you can find more in the Wikipedia article on the RSA challenge numbers. Okay, so this would presumably take even more CPU core years, even though once the factors are given to you, a computer could multiply x and y in an instant. Okay, and of course, if we could factor integers easily, we could break all RSA-based crypto. And if P equals NP, then public key crypto, at least as we know it, would need substantial revision. I mean, I'm tempted to say public key cryptography would be dead, but there are always weird caveats, and there's always an element of unpredictability in what's possible in computer science and math. So at the very least, we need to revisit and revise our foundations. Okay, so one of the most important NP problems is Boolean satisfiability, or the KSAT problem. So in this problem, we're given a Boolean formula, which is a big logical AND over some clauses, C1 through Cm. So there's m clauses over n variables, x1 through xn. And each of these clauses is an OR of some variables or negations. And we are allowed to go up to k. So we think of k as some fixed constant, like 3. Okay? So each of these y's is a variable or is negation for something. And this is known as conjunctive normal form. And the problem is to just determine whether there's a true-false assignment that makes the formula true, makes all these different clauses true simultaneously, or answer no if there's no such satisfying assignment. Right? And here's an example, just to be clear. So the middle clause is satisfied by x equals false, the first by y equals true, and the last by z equals false. Okay? So just to illustrate. Now, the brute force algorithm can solve this by trying all 2 to the n possible assignments. And P versus NP can be thought of as some formalization of the question, is there a faster way? Is there something better than just sort of trying all the possible true-false assignments? Right? We're encoding some kind of search space here, and we want to know, if I give you the true-false assignment, you can check it. But we want to know how efficiently you can find it. Okay? And the Cook-Levin theorem shows that for all k at least 3, k-sat is NP complete. So the entire difficulty of P versus NP is the NP completeness means that the entire difficulty is encoded in k-sat. Okay, so P is from NP if and only if k-sat is not in polynomial time. Right? So we could just study k-sat and try to understand how difficult it is, and that could give us a handle on P from NP. Okay? So the next thing I want to say about the Cook-Levin theorem is it's actually something of a triumph for practice. Okay? So the Cook-Levin theorem says that every NP problem can be efficiently encoded in this programming language, CNF SAT, so conjunctive normal form satisfiability. Okay? And so this was initially viewed as a result in the difficulty of SAT. Therefore, that's why it's called NP hard. Somehow makes it a hard problem. But the Cook-Levin theorem has turned out to be an extremely useful practical tool because there was a revolution in practical SAT solving that began in the early 2000s, starting with the graph solver, the shaft solver, and so on. So there's a nice survey from last year in Communications of the ACM on the SAT revolution. And so they're now incredibly well-engineered SAT solvers that can be used in principle for solving any NP problem. So for many practical problems, the fastest way we know how to solve them is to convert them into this conjunctive normal form and then run a SAT solver. I'm not joking. Yeah, so the Cook-Levin theorem turns out to be extremely useful in practice. Like, that's what you're doing. You're running the Cook-Levin theorem on your problem, converting it to some CNF thing and then running a SAT solver. Okay, so is SAT a solved problem? Are we done? No. Okay. So it's easy to cook up examples where practical SAT solvers essentially run for eons. So like examples which encode integer factorization, for example, are extremely difficult for SAT solvers. But these examples aren't esoteric, and so I've stumbled upon some myself in the course of some work that I've been doing recently, trying to understand something totally different by running SAT solvers. So indeed, we still believe that P is in from NP. Like, SAT is not sort of magically solved, but we want to get a handle on exactly how strongly can we believe, like, in limitations on solving SAT. So exactly how hard is the SAT problem? So P from NP just says that 3-SAT is not solvable in some polynomial, in polynomial time. So into the k time for all constants k. Okay, I mean, the first thing we could ask is, well, we know that 2 to the n can be done, right, trying all the possible assignments. Does 3-SAT require 2 to the n time? This is sort of the first thing you can ask. Like, or is there some way something clever you can do there? And so already we can say no. Like, it doesn't require 2 to the n time. There is something faster you can do. And it's a very simple strategy you can try. So you're given a clause, say x or y or z. There's only 7 out of 8 satisfying assignments to these, right? There's 8 possible assignments. Only 7 of them satisfy. All false does not satisfy. So you can just recurse on just those 7 assignments. So you plug in one of 7 assignments, or your 3 variables, and recurse, right? Brute force would have had to plug in all 8 and recurse. Like you plug them in, you remove those 3 variables, and you continue. So this simple idea already gives you some algorithm which beats brute force, maybe not by very much, about 1.9 to the n. But the point is that 2 to the n is not optimal. So there's already something going on in this NP-complete problem that can be exploited. And similarly, you could extend this for k-sat. In any clause of length k, there's 2 to the k minus 1 satisfying assignments out of 2 to the k. And so you can get something faster than 2 to the n, okay? So the conclusion we can draw here is that for all constants k, there's some delta less than 1, so that k-sat is in 2 to the delta n times. So you can always beat brute force by a little bit, okay? But as k goes to infinity, as k gets bigger and bigger, this delta actually goes to 1. So as k is increasing here, this is going to just become 2 to the n again. Okay, this is going to get closer and closer and closer to 2 to the n. And all known k-sat algorithms, including ones which are adapted, mimicking what happens in practice, like backtracking type algorithms, dynamic programming, local search, algebraic algorithms, they all have this deficiency. They all have a similar type of deficiency that somehow they can't get around this as the width of your clauses gets larger and larger, the number of ORs, the number of variables in your OR you allow, it's going to become more like 2 to the n. All right? So this has led to several conjectures about the difficulty of SAT. So there's 2 major conjectures about SAT going beyond Peter and Impey that people have studied starting in the late 90s. So the first starts with the question, is the 3-SAT problem solvable in 2 to the epsilon n time for every constant epsilon? So it's basically asking whether 3-SAT is solvable in sub-exponential time, right? We know that you can get 1.9 to the n, and in fact, you can get something like 1.31 to the n. This is the best known. But could you keep going? Could you get, 1.000001 to the n? I mean, at some point, this could become very practical. And it's not going to be much different between polynomial except for extremely large n. So the exponential time hypothesis conjectures the answer is no. And what do we mean? We mean that there is some epsilon so that 3-SAT is not in 1 plus epsilon to the n time, okay? If you don't want to think about the epsilons, you can just think of it as 3-SAT can't be solved in 1.00000001 to the n for some number of zeros. You can't just keep reducing the base of the exponent arbitrarily. Like there's going to be some point at which you cannot solve it faster. All right? So it's much stronger than Peter and Impey. So it's not only is it assumed to be not in polynomial time, there's actually some exponential lower bound assertion. Okay? Another question that's come up is k-sat solvable to the delta n time for some universal delta? So I mean some delta independent of k. So like maybe a 0.9, like regardless of the value of k. All right? So the strong exponential time hypothesis conjectures the answer is no, okay? So no matter what delta you want to get by with, subtract from in the base of the exponent, there is some k so that k-sat will not be solvable in 2 minus delta to the n time. Getting rid of the deltas and the k's, you can just think of this hypothesis saying CNF sat, so without any restrictions on k, so it's just the ands of ors. This can't be solved in 1.99999 to the n time for all numbers of 9s. So like you just cannot improve the base of the exponent at all. All right? All right, so it's a theorem that strong ETH implies ETH. This is not obvious. Let me not get into it. But ETH and strong ETH are totally consistent with our knowledge of SAT, even knowing what real-world SAT solvers can do. Okay? Because there are many, many cases in which SAT solvers, even the practical ones, will break down and just essentially just run forever as far as we can tell. Okay? Okay, so what is the use of ETH and strong ETH? Well, for one, ETH has been used to show strong lower bounds for other NP problems. And this is somewhat expected. Right? So there's like a large number of other NP problems like clique, or vertex cover, bisection, and so on. You know, and if you assume that 3-sat needs some exponential amount of time, all these others also need some exponential amount of time, but the exponents can vary. And so some problems can actually end up being easier than others. And the whole notion of NP completeness kind of shatters a little bit, and some problems turn out to have faster algorithms than others. Okay, well that's just with ETH. With strong ETH, it's much more interesting. So my personal opinion is that I believe strong ETH is false, that there is a faster sat algorithm, but ETH, meh, I don't know. Yeah, so my belief in the negation of strong ETH is the minority opinion, I should say. But I say really, okay, it's small font. The chances I'll be proved in my lifetime are nil. I mean, first you have to separate P from NP, and then you have to prove an exponential lower bound. So I think I'm, you know, like you're not gonna, it's fine. Like you're not gonna prove me wrong. But like, on the other hand, I'm not trolling, okay? Like, so I mean, I should make it clear that I'm not trolling. So like my dogged pursuit of a faster algorithm for CNF-SAT over 20 years has failed so far. So why do I keep doing it? That's a good question. So even if strong ETH is true, my belief in its negation has led me to many ideas and results that I would have never found otherwise, okay? So belief has been sort of a catalyst or maybe even a muse for my research. So it's like belief in a fact, not necessarily because you have faith in a particular truth value, but belief like as some way of getting you thinking about things. So I found that if I pretend strong ETH is false, and I have to visualize what the algorithm could look like, what it could possibly do, it has to look very different from anything used in practice, anything ever conceived, I get new ideas. And we all want to get new ideas, don't we? We all like and interesting ideas. And if I try to visualize what its consequences would be, negating it, I get ideas, okay? So why not believe that it's false, right? If it helps you get ideas about research, then, you know, all for it. You're not gonna prove me wrong anyway, so it's fine. You know what I mean? So okay, so that's sort of the high-level overview of what's going to happen in this talk. So the outline is going to be one failed approach to refuting strong ETH, which led to an area now known as fine-grained complexity. And then so what? So because you might be asking, so what? Like, why are you trying to find a 1.9 time algorithm? This is a question I asked myself, okay? I've asked myself this question before. And I got another failed approach, but this led to me becoming a circuit complexity theorist. I didn't necessarily want to, but it happened because I mean if you can prove something, why not prove it, right? Like this is my belief. Okay, so and then if I have time at the end, I'll talk about a new, not yet failed approach, as far as I know. Yeah, all right, great. So the problem with like asserting a very strong lower bound, like there is no CNF-SAT algorithm running in 1.999 in the time, is that algorithms can do very unexpected things. They can be magical, okay? So in grad school, I became enamored of a magical algorithm of Itai and Rode for finding triangles in graphs, okay? So imagine you've got an n-node graph. You want to find an object like this, all 3 nodes with 3 edges supported. Obviously, there's an order n cubed time algorithm. Just try all the triples and see if there's a triangle there, if all the 3 edges are supported. Yeah, and it just seems like, okay, this is just some combinatorial search problem, right? It's MP-like. If I show you where the triangle is, then you can verify it. But like, do you have to actually try all the triples or not, right? So it's like, can you beat the brute force, the simple algorithm, or not? Okay, well, it turns out you can. So, and you can use matrix multiplication to do this. So let omega, which turns out to be less than 2.372, be the smallest real so that n by n matrix multiplication can be done in n to the omega additions and multiplications. So think of it as like n to the 2.4, right? The obvious algorithm for n by n multiplication will take order n cubed time to compute all the different inner products for all the n squared entries. So I believe in sort of a conservation of magic principle. If you find something that's sufficiently magical in one domain, it will yield magical solutions in other domains. I mean, like we already saw this with the Cook-Levin theorem, the triumph of the Cook-Levin theorem in SAT solvers, right? So it works in mathematics and in real life, okay? All right. So here's the theorem. So on n-node graphs, triangles can actually be found in n to the 2.4 time, okay? Or so somehow you can avoid like searching this whole space, avoid looking at all the triples. And yeah, it's not at all clear why, like, or how you should be able to do this. So here's the proof. It's a really short proof, okay? Okay, I promise, okay? So, because there's not much room, you see. So let A be the n by n adjacent matrix of our graph, and let B be the product of A with itself. Okay, we just take the matrix, multiply it by itself, all right? So now I claim that G has a triangle if and only if there's I and J such that Aij is 1 and Bij is non-zero, right? Okay, so these are just, two nodes, I and J, like in our graph. All right, so let's see why that's true. So suppose like, B is the product of the matrix with itself. So it looks like the sum over all K of Aik times Akj. And I'm claiming it's non-zero, right? So if that's true, then in the JC matrix, I must have an edge from I to K and an edge from K to J for some K, right? The only way this is non-zero, because these are all 0, 1s, is that there has to be some K for which this is a 1 and this is a 1, right? Okay, but if Aij is also 1, then I get the other edge, okay? So this is exactly the condition for whether a triangle is in the graph or not. It's exactly the condition, right? But I can do matrix multiplication faster than n cubed. I can do it in the 2.4 time, so I'm done, all right? Very simple, magical way of somehow avoiding trying all the possible triples, okay? All right, so could there be a magical algorithm for SAT like this? So could one embed like a formula into like a very large graph so that finding a triangle in the graph somehow corresponds to finding a satisfying assignment? Okay, so let's think about what on earth could this mean? Like what could it boil down to? So like suppose I have a formula, a CNF formula on K variables, and I want to reduce it to like triangle finding on n equals order 2 to the K over 3 nodes. Okay, so if I could do that, right? So if I could reduce it to n to the, so like 2 to the K over 3 nodes, right? So if we think of n cubed as the search space for triangle, 2 to the K is the search space, right? When we're trying to solve CNF SAT on K variables. So then n to the omega, like if I can solve triangle n to the omega, that means I'm solving this triangle instance in 1.74 to the K time. Okay, so that would beat exhaustive search. All right. Okay, this approach completely failed. All right, like edges can only encode so much, and they definitely, as far as I can tell, can't encode CNFs. All right. However, edges can encode constraints on pairs of variables. Okay. Well, 2SAT is already solved in polynomial time, so that's not so useful. However, you can use it to solve problems like max cut and max 2SAT. So the problem of finding a cut in an n-node graph that maximizes the number of edges crossing from one side of the cut to the other can be solved faster than 2 to the n using this approach. And so I was still trying to understand, like, okay, could I reduce a triangle finding? Could I reduce to something magical? So what I did was I found other simple polynomial time problems. Okay, triangle is just one of them. So like other problems, so that if I could solve them faster than an obvious algorithm, then I could also solve CNF SAT faster, okay? So this is one of some of the first results in the area that's now known as fine-grained complexity. Okay, so here's the first problem I looked at. It's called orthogonal vectors. So we're given a set of n binary d-dimensional vectors. We don't know if there are 2 with inner product equal to 0. All right, so I have a collection of vectors like this. Right, I want to find 2 with inner product equal to 0. Well, that means that in every component, if I look at these pairs, there's at least 1 0 in each of the components, right, in order to get an inner product of 0. Right? So I'm really just looking for things with a disjoint set of ones. Like there's some set of ones here, some set of ones here, they're disjoint. So like here, for example, there's an orthogonal pair, right? You know, and it's just, like, you know, you kind of have to look to, you know, I try to make it a little difficult to find, I don't know. Like, so, you got to look at that component to see. So the trivial algorithm, right, is just try all the possible pairs and then compute the inner product. Right? It's d dimensions, so let's see. So you know, for d constant, this is not a hard problem. But for d, you know, like even order log n or log squared, it's some sort of high-dimensional problem, and it becomes difficult to reason about. It's very simple, but it's surprisingly tricky. Surprisingly tricky to think about. And so what I showed was that if you can improve this trivial algorithm, right, if you could, say, get into the 2 minus epsilon time for even like log squared dimensions, then you would refute the strongest mutual hypothesis. You would have C and F set on n variables, in this case n squared clauses, solvable in, you know, some exponent which will be you know, less than 1. So 2 to the delta n for some delta less than 1. Okay? All right, so what's going on here is that I'm taking a formula, right, and I'm splitting its variables into 2 halves, and then sort of making vectors for all the possible partial assignments in those 2 halves. And these vectors, I'm going to set them up so that there's an orthogonal pair if and only if I take this partial assignment from 1 half of the variables and this partial assignment from the other half of the variables, they match up and make a satisfying assignment. Okay? So this is just a very high-level idea of how you would show this thing. But what's strange here is that, you know, we're talking about a polynomial time solvable problem, a quadratic time solvable problem, and we're saying it's actually harder to improve on this quadratic time solvable problem than it is to improve on the 2 to the n running time of C and F set, right? Like if you can solve this quadratic time thing faster, you solve C and F set faster. So it's a little bit weird. It's so counterintuitive that somehow a quadratic time problem became harder than an NP hard problem. Okay, well, I mean, we're talking about the time complexity. That's the trick here. Is because we're only thinking about the time complexity, and we're just trying to beat exhaustive search. Okay? Okay, so another problem, which is very related, but maybe closer to practice, is partial match queries. So I give you a database of n strings, which are d bits long, and I'm given n queries with wildcards. Is there a query that matches a string in the database? Okay, so we have a bunch of queries. These are over 0, 1 with a wildcard. It means I don't care. Means here you could put a 0, you could put a 1, I don't care. You could put a 0, put a 1, I don't care. And over here, I've got a database of strings, just strings, okay? So I want to get a partial match. So like, for example, like, here's a partial match. I could fill in 1 and 0 and 0, okay? All right? So I just want to know, like, I set it up so that I just want to find some query that matches some string, but it turns out that getting a better algorithm for this, an algorithm better than the obvious one for this, would get you one that would solve each query faster overall than just trying them all. Okay? But so this is a very natural problem, very, very natural problem. The trivial algorithm is, again, quadratic time times d to look at the d-bit strings. Without the wildcards, this is a very trivial problem. Or without the wildcards, you could just sort the whole thing, you know, and then just look for duplicates, you know, like that's all, right? So it's the wildcards that make the problem interesting, all right? And so what I showed was also that if this partial match problem could be solved in subquadratic time, then you could also solve the SAT problem faster than to the n. Okay? Yeah, in fact, this problem is basically equivalent to the orthogonal vectors problem, it turns out, in terms of its fine-grained complexity. They're essentially equivalent. Okay. Another problem, just sort of one more problem to mention that happens to do with, you know, something else is on graphs. So I couldn't, right, get something to work with triangles, but I found another graph problem for which solving it faster would give you a faster SAT algorithm. So this is the k-dominating set problem. So here I'm given a graph, and I want to know if there's a set of vertices of size k, so that the set, along with its neighborhood, is the entire vertex set. So I want a small set, S, such that every other vertex in the graph, it has a neighbor of something in that set. Right? So for example, here, there's a dominating set of size 2. If you look at all the other vertices, they're a neighbor of one of these two circled vertices. Right? So it's known that this is solvable in about into the k time using some fast matrix multiplication tricks. And I show that if there's any k and any epsilon, so that you can get into the k minus epsilon time for this problem, then you can also solve SAT faster. Okay? And so this is just yet another result along these lines. So trying to solve dominating set would actually let you solve the problem. Triangles, somehow not expressive enough. And there are many more such theorems, but I failed to solve any of those problems faster, okay? Like utter failure, okay? I cooked up all these different ways to try to solve SAT, and they all broke, okay? So what did I do? Well, I turned it around. Every failure is an opportunity, I guess, maybe. And I said, well, strong ETH makes predictions beyond just NP problems, okay? So if you take the contrapositives over the last 3 slides, okay, I said, if you can solve this OV problem faster, you refute strong ETH. If you solve this partial match problem faster, you refute strong ETH. If you solve dominating set faster, you refute strong ETH. Okay, take the contrapositive. It says the strong integral time hypothesis implies that orthogonal vectors needs about quadratic time, partial match needs about quadratic time, k dominating set needs about into k time. Okay? And so it turns out for many fundamental polynomial time problems, improving on the best algorithm, even slightly, would give us a faster SAT algorithm. So this hypothesis predicts the optimality of many known polynomial time algorithms. So this led to a theory of hardness within P. So like there's a lot of quadratic time problems in practice because n is so large, n squared is intractable. You want like n log n, or you want to know, can I ever improve the exponent? Can I get n to the 1.9? Like anything would be better, right? So this provides like a whole hardness theory for thinking about such problems that didn't exist before, okay? So if we start with the hypothesis that CNF SAT needs 2 to the 1 minus delta n time for every tiny delta, we get that orthogonal vectors needs in the 2 minus epsilon time for every epsilon. And from that, we can conclude the optimality of many, many quadratic time problems. There's dozens more references here. I included some of them here, but there's diameter and sparse graphs, various distance measures, longest common subsequence, edit distance, trying to find the edit distance between 2 strings of length n. Like there's very simple textbook algorithms for all these different problems. And assuming, say, this orthogonal vectors problem is difficult, all these are difficult. So it turns out this OV problem, orthogonal vectors, is some key bottleneck problem. If we can't solve it faster, we can't hope to solve any of these other problems faster. So assuming this strong ETH, there's dozens of natural and important problems whose simple quadratic time algorithms cannot be improved. There's also cubic time problems and into the 4 type problems. I just want to restrict to like a few things here. Okay, there are so many more developments in fine-grained complexity beyond this, but there's even more to say about SAT. Yeah, so this edit distance thing was quite celebrated. I think there was even an article in the Boston Globe about it. Like, I guess edit distance is a big problem. Okay, great. So sorry?
It's slow news day.
Slow news day. Oh yeah, it could be. I mean, yeah. Okay. I don't know what to say. I guess I was at Stanford then, so I guess it's fine. Okay. Anyway. Yeah, so now I want to go to so what, because you're probably asking this question too. And another fail approach, okay? So that's kind of like what I was doing as a grad student, trying to find ways to solve this CNF SAT thing and having it break. Okay, I did other things as a grad student, thankfully. But But yeah, so there's many interesting ways to beat exhaustive search for NP-hard problems. I was talking about SAT, but there's a whole theory of these things, okay? I'm not gonna list all these out, but maybe you can see a problem you've seen before, and there's a faster algorithm for it than the obvious algorithm, okay? And okay, so I did a postdoc, as Paul said, at the Institute for Advanced Study. And I was trying to get people interested in these algorithmic problems because I don't know. There's a trivial algorithm, there's an obvious algorithm. I want to know if there's a faster one. It just seemed like a very basic question to understand. But yeah, I mean, it was very difficult to get anyone else interested. And this really made me wonder, and maybe some of you have been thinking, so what, okay? So like, they still take exponential time. Like if I get like 1.99 to the n time, like what did I do? What did I really do if I go from 2 to the n to 1.99 to the n time? Like, but still like, it bothered me. Like I have the feeling that the problem of beating exhaustive search is very fundamental, but I don't know why it's fundamental. And so I need to prove a theorem to try to convince myself that what I'm thinking about is actually fundamental and important. So I asked myself, suppose I could get slightly faster algorithms for every NP problem. Like just whatever NP problem I want, let's say. Would the rest of theory change? Like would anything change? Besides like, like these tables or whatever, okay? Like, could I resolve a problem in a different area that people care about for a completely different reason? Like, people who actually hate these algorithms would have to start caring. This is like, yeah, so this is what I soul searching in my postdoc, really. So I came up with something, okay, like I read many textbooks and many papers, just said, okay, suppose strong ETH is false here, 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 what happens? Like, what happens to complexity theory? Okay, so I found something, which I hope to describe to you at some level of detail. Okay, so we're going to start with a circuit satisfiability problem. So here it's just a generalization of that CNF case. We're given a logical circuit, let's say composed of ands and ors and NOT gates. We want to know if there's an assignment to its inputs that makes the circuit print 1. Okay, and Cook-Levin still tells us this is NP complete. We can still solve it by brute force, exhaustive search. And so the question is, well, for what kinds of circuits is there a faster algorithm? Like for 3CNF, for 3SAT, we know faster algorithms. For KSAT, we know some things. But like, could there be algorithms for general circuits? And if so, like, if you've got a faster SAT algorithm, this must tell us something about what that circuit can do. So this was some weird intuition that I had that I'm still trying to understand. I mean, there are proofs of confirming the intuition. But the question is, like, are there any consequences for how efficiently those circuits can compute functions? Like, I have an algorithm, it's analyzing a circuit, it can quickly tell me, or quickly, faster than 2 to the n, whether or not it's satisfiable. I must have done something to analyze these circuits. I must have said for every possible circuit, I can analyze it faster than just trying all the inputs and getting the outputs and figuring something out. So I must have done something. Like, I must have analyzed all the circuits in some interesting way. So what did I do? Okay, this is the question I asked myself. So in general, like, it's a major open problem as to which Boolean functions need very large circuits, okay? And, well, nearly all of them do. So, like, if you pick a random function, it's going to require huge circuits. So a theorem of Shannon says that with high probability, if you just choose a completely random n-bit to 1-bit function, so just pick, like, flip 2 to the n, mutually independent coins, unbiased, it will require exponential size circuits. It will require enormous size circuits, right? You flip 2 to the n coins by a counting argument. There's just too few small circuits to encode all of the 2 to the n possible Boolean functions. So there's going to be some, in fact, most functions are not going to have small circuits just by counting, all right? So one of the major questions in circuit complexity theory is which natural functions exhibit this kind of exponential behavior. Like could SAT or some NP hard problem need large circuits? And why? Why would you ask this question? I mean, besides like just trying to understand what circuits can and can't do. So there's many reasons why one might study circuit lower bounds. But one reason you might not know about is that circuit lower bounds can be used to de-randomize algorithms. So a celebrated theorem shows if there's a function, so from arbitrary bit strings to bits, computable in exponential time, but if we look at finite slices of it, restricted to n-bit inputs, it doesn't have circuits of size, say, 2 to the epsilon n, then we can show that randomized time is polynomially equivalent to deterministic time. There's like a generic way to just remove the randomness from all algorithms. And there are many other results in this direction. The idea is that if a function looks random to all circuits, like somehow like you can't use circuits to compress what it's doing, you can construct a pseudorandom generator and replace true randomness in efficient computation, okay? And so this sort of assumption is widely believed. So this would be like an exponential time computable function that requires, on finite slices of it, restricted to n bits, exponential circuit complexity, right? So this would be one major consequence of getting circuit lower bounds, being able to de-randomize. But there's others too, other reasons too. So what I was able to show is that faster circuit set algorithms actually imply circuit lower bounds. They actually do imply like lower bounds in a very generic way. Okay, so let me just try to show you how the quantifiers match up. So suppose there exists something that looks like a Turing machine, which is a slightly faster than 2 to the n times circuit set algorithm. So 2 to the n divided by, say, n to the log n. So this is actually not nearly as good as 1.9 to the n. This is much worse. It's just a slight improvement over brute force. And for all the possible circuits you might write on its tape, it can tell you whether it's sat, yes or no. And somehow it's not running into the n time. It's somehow avoiding exhaustive search, all right? Right, so you could take this algorithm and use it to construct some interesting function definable with respect to Turing machines so that for all finite slices, almost every slice of this function requires large circuit complexity, okay? So there's a program that's been developed whereby slightly faster circuit set algorithms, just slightly faster than exhaustive search, can lead to impossibility results for circuits, okay? All right, so this is a sort of unexpected thing. So we knew that lower bounds could be used to get algorithms like de-randomize, but in fact you can go in the other direction. You can show that algorithms can be used to prove lower bounds. All right, so analogous results hold for formulas. Like if you had a formula set algorithm, you get formula lower bounds and many other circuit classes, okay? So another failure led to another circuit lower bound. So I found some cool consequences of improving exhaustive search, like you would get these lower bounds, but no one believed these results could prove a circuit lower bound. So they're like, wow, if you could improve over exhaustive search for circuit set, you could prove circuit complexity lower bounds. Great, well since we're never going to prove circuit complexity lower bounds, this means we'll never improve over exhaustive search. Wow, that's such a nice theorem. You know, like, so I had to start learning more about circuit complexity myself, I guess. And in 2010, like I had yet another approach to solving CNF set. The details don't matter. You can read that part if you want. If you don't want, that's fine. But it failed, okay? The main part is it failed. This is the worst failure. I got CNF set algorithms are actually much worse than like than what was known. Like they were terrible. Okay, but I was staring at it and I was looking at this approach, you know, using some algebraic methods, and I was thinking, actually, these work not only for CNF, but they work for like more general expressions. They work for something more general than just like ands of ors. They can work for ands of ors of ands and things like this. They can work for things, and so what I showed was that SAT for some class, let's just call ACC annoying circuit class for the purpose of this talk. Just annoying circuit class, something like wide open, extremely difficult to analyze. So I was able to get a SAT algorithm for it. They ran 2 to the n minus n to the epsilon time for some like tiny epsilon depending on some parameters in circuit. It's actually very bad, like in terms of like a SAT algorithm, like very bad. However, the next day I proved that this implies the circuit lower bound. That from this you will get that there's functions, for example, in X that are not computable by these annoying circuits, all right? And this is what Paul was referring to, this log jam, or 20, 30-year log jam. So I guess sometimes, even if you fail, you can get a Gödel prize. You just have to be lucky or something. I don't know, whatever. Okay, so now there's an entire literature of circuit complexity lower bounds which proceed by proving one of these nice arrows and then designing an appropriate SAT algorithm. So I think everyone working on SAT solvers should know this fact. If you come up with a way to slightly beat exhaustive search for SAT on, like, maybe formulas or whatever, you are actually proving a major complexity theory result. Okay, so you just beware. Okay, if you're like thinking about SAT solving. Okay. Okay, so why? Why on earth should this be true? So let me try to give you some intuition about why. I mean, it can only be high level at this point, especially given the lack of time I have. So the idea is that faster circuit SAT algorithms reveal a weakness of small circuits. So in other words, like, if a circuit is trying to compute the all zeros function, right, it's unsatisfiable, it always outputs 0. If you've got an algorithm which can analyze this circuit and tell you faster than just trying all possible assignments, it's somehow not obfuscating as well as a black box could. Right? So if I've got a black box and I just can only probe inputs and get outputs to it versus a circuit SAT algorithm running in, say, 2 to the n over n the 10th time, right? The black box is always going to take at least 2 to the n time, right? Like, for any algorithm computing SAT that can only just get, inputs, outputs, you can always rig up some box so that the algorithm is going to have to call this box 2 to the n times, right? So somehow, you can just have the box like look at what the algorithm does and just keep saying 0, 0, 0, right? So somehow, like, being able to analyze the circuit and do faster than 2 to the n is a weakness in this circuit class. It means it's something weak. It cannot hide a satisfying assignment as well as a black box can. Okay? So somehow a faster circuit SAT algorithm demonstrates a concrete difference between the sort of white box circuit problem where you get to see the whole circuit and the black box problem where the circuit is hidden. So somehow, like, the circuit cannot hide the satisfying assignment. I have a new not yet failed approach. You're right. So another version of this. So this is actually some new work to appear in Fox next week about Sierpinski triangles, shallow neural nets, and SAT. The bottom line of this is that at least one of the following things are true. Okay, so we don't understand neural nets. So this is neural nets with a sign activation function. It has some linear combination of my inputs, and I want to know whether it's at least a certain threshold. If this is true, it fires 1. Otherwise, it fires 0. So either a very simple function, like basically an OR of ands, needs exponential size depth 2 neural nets. So I'm just computing a linear combination here and have some hidden layer here. It's a wide open problem to get any sort of interesting lower bound on these guys. So either this is just true, or there's no quantum advantage for SAT solving. So there's a deterministic algorithm for CNS SAT running in square root of 2 to the n time, as fast as Grover's search. So like at least one of these two things is true. So a major refutation of SAT. So yeah. And it's weird because like this is actually about circuit complexity, and this is about an algorithm. So this algorithm does, it's not working like a circuit. It has some fixed code. All right. So let me see here. So it's a curious consequence of shallow neural nets. So there's this function called the disjointness function, so and of ORs. If it has a depth 2 neural net circuit family with subexponential many wires, then KSAT can be solved in 2 to the n over 2. Very strong refutation of Seth. So as a corollary, we get a win-win circuit complexity lower bound. Either this very simple function, these exponential size depth 2 neural nets, or we get new circuit lower bounds from having these faster SAT algorithms like I was describing before. So you get some algorithm for CNF SAT like this, you will be able to prove a circuit lower bound a different way. Okay? And the proof, either Seth is true or Seth is false. Okay? And then for Seth is false, you need this arrow. Okay. All right. Great. All right, so let me conclude. So although this strong ETH remains unfalsified for now, many interesting results and directions were forged in the process, probably ultimately more important than refuting the strong ideas as far as I know. So one open problem for everyone is, can we find opportunity in failures? Of course, I've had many, many, many more failures, which were simply failures, okay, with no apparent opportunities. I mean, complexity theory is a tough subject. So, I mean, I want to deliberately search for scenarios where no matter what, something interesting can be found. It seems like the only way to proceed and not accidentally waste years trying to push the wrong thing. So another question for everyone, what are the catalysts for your research? So like, what are the muses that help you generate ideas? Okay, that's all. Thank you.
Thank you for a fantastic talk. There is a bit of time for a couple of questions. Yes?
I'm curious about the orthogonal pairs of vectors. If the dimension is large, let's say square root of n or third root of n, is there anything better than n squared times d?
Oh, yeah. So if the dimension is square root of n, then you can use fast matrix multiplication. So you're asking whether there's something better than n to the 2.5. Right. Yeah, you can think of them as two matrices, n by square root of n, square root of n by n, and you multiply them. Yeah. And known bounds on rectangular matrix multiplication will get you something faster than 2.5. Yeah, so in really large dimension, you can beat that, at least. But yeah, like for us, we care about the case where the dimension's like polylogarithmic and we want to beat n squared. But yeah, it's also a good regime, too.
So with the triangle finding,
Yeah.
right, if you take like trace of a cubed, now you count the number of triangles.
Yeah, you can even count them. Yep.
Right. In the other examples, do those lead for faster problems for sharp P or something of this nature?
Oh, yeah, I didn't even get to that. So, yeah, so you're asking, like, do you get faster algorithms for sharp P and stuff like that? Yeah, so it is known that if you manage to...
Maybe you should explain sharp P.
Oh, sharp P is like counting the number of satisfying assignments, counting the number of solutions to an NP problem. Like I have some way of verifying and I want to count the total number of solutions, right? It seems like a much harder problem. Yeah, so, I mean, there are situations where getting a counting set algorithm for like a class would actually lift to get you a lower bound for a larger class. So this is some relatively recent work. So it's known that counting can actually buy you more. Like if on the one side you didn't solve circuit set, but you were able to count, you actually get stronger things. Is this what you're? Yeah. Yeah, I can point you to the paper later.
I remember one of the previous slides, you talked about, like, the thing you're doing right now, it's about the quantum advantage.
Yeah.
Right? So I was, can you expand on that a little?
Oh, yeah, I guess I was just saying that, I'll just go back to this slide. So I was saying either you have this exponential size lower bound from neural nets, or you get this deterministic algorithm for CNF set that runs in 2 to the n over 2 time. By saying there's no quantum advantage, I'm just saying that, like, we know quantumly you can get 2 to the n over 2 time. But if we get a deterministic algorithm, it would essentially match that. That's all I meant by saying there's no quantum advantage. Yeah. And what's happening is that, like, you're saying, like, look, if this simple function actually had sub-exponential size depth of neural nets, I can use this to solve SAT faster, like way faster. So that's actually what's happening, right? So if you think of it, so if the first one is false, have some sub-exponential size circuit, I can use this to solve the SAT problem faster.
Other questions? Let's thank Ryan again.